Welcome back, everyone. In this video, we're going to continue learning from Chapter 6, Lesson 3. We're going to be focusing on understanding lattice energy and how we can use the periodic table to predict relative lattice energies and melting points of ionic compounds. So, we talked about how ionic bonds form when elements exchange electrons to form separate ions and have a completed octet. So the elements involved will either gain or lose electrons in order to obtain the noble gas configuration closest to them. So if we take a look at this process, then for sodium, if we can talk about the ionization energy of the sodium atom, and that requires just under 500 kilojoules per mole. We are pairing that with the electron affinity for the chlorine atom, which gives off just under 350 kilojoules per mole. That means then that this process would require an input of just under 150 kilojoules per mole. However, if instead of doing this in the gas phase, or rather, if we take the elemental forms of sodium and chlorine and then combine them to form solid sodium chloride, we see that this gives off actually about 400 kilojoules per mole. So what is the cause of this discrepancy? Why in one scenario do we require a relatively large input of energy, whereas in another scenario, it gives off a lot of energy? So the difference we shall see is because of the ionic bonding that occurs, that this is a very favorable stabilizing interaction. So the fact that up above, we were taking the elements and forming loose ions in the gas phase is not very favorable. However, when they precipitate down, condense down into the solid phase, then that gives off a lot of energy. And that is what is the driving force for these types of reactions. So let's talk about that energy. We call the energy that essentially binds two ions together, we call that the lattice energy. This is essentially the amount of energy that would be required if we wanted to take a solid compound and break it apart into its ions in the gas phase. So the lattice energy of sodium chloride, about 800 kilojoules per mole, is the energy that would be required to take a mole of sodium chloride and to break it apart into its ions and to turn those ions into gas phase. And we can think about the lattice energy in terms of Coulomb's law, which we've looked at many times already this semester. And so in general, the higher the lattice energy, the more the ions are attracted to each other and the stronger the ionic bonds. That's going to lead then to higher melting points or boiling points. So what does this look like? How do we actually evaluate this? So let's take a look first at differences in lattice energy based on the charge of the species involved. So the lattice energy of lithium chloride is about 860 kilojoules per mole. Strontium oxide is about 4 times that much. Now, when we take a look at Coulomb's law, it says that the energy of the attraction is directly proportional to the product of the charges over the distance between them. We note that the radii between the nuclei is almost identical. It's only 1 picometer difference out of 250 or so picometers. So it's a very, very small difference. And so we can attribute the difference in the lattice energy solely to the difference in the ionic charges. When we look at the charge of the species, lithium and chlorine each have a charge of +1 or -1 respectively. Strontium has a +2 charge. oxygen has a -2 charge. Therefore, the numerator in this equation for strontium oxide is 4 times the value of that for lithium chloride. This prediction holds out really well, and so we see that the actual lattice energy is pretty close to 4 times the value for strontium oxide versus lithium chloride. So our first way to predict and compare lattice energies for relatively similar sized ionic compounds is by looking at the charge of those species. The second thing to look at is within ionic compounds that have the same charge, look at the difference in size. So we have here 3 different metals that are combined with chloride, and so because they all have the same charge, we don't need to consider the charge of the ionic compound, but we can see that they have relatively different radii. And so when we look at the radii, keeping in mind that the larger the radius, or the larger the distance, the smaller the energy of interaction between them, that the predicted lattice energies go down as the ionic radii get larger. And if we take a look at the actual lattice energies, then this confirms it. The lattice energy for sodium chloride is about 90% the lattice energy of lithium chloride. And the lattice energy for potassium chloride is about 80% the lattice energy for lithium chloride. And so what we see here in the end is that the value for the radii do not change as dramatically as the value for the charges. We went from a charge of +1 and -1 to +2, -2, and that changed our lattice energy by a factor of 4. Whereas when we look at the radii, those are changing by maybe 10, 20%. And so the lattice energies are only going to change by 10 or 20%. So the first thing you want to do when ranking lattice energies is take a look and rank them based on their charges. Then, if you have 2 sets of ionic compounds with the same sets of charges, then you start to look at the ionic radii. All right, let's see if you can figure this out then. Rank the following compounds in order of increasing lattice energy. Pause the video and try this on your own first. Welcome back. So, if we want to think about lattice energy, we need to think about Coulomb's law. Coulomb's law states that we need to look at the charges and the distance between those charges. So, using the periodic table, you should be able to predict the charge of each of the ions involved. What we see here then is that we have a set of charges where the magnitude of those charges is much larger than the others. And so in terms of lattice energy, we know that the aluminum nitride is the greatest because its charge pairing has the highest magnitude. Then we know that barium sulfide is next. Again, because charge is the better predictor, your first step is to evaluate the lattice energies based on the charges. We know then, now what we need to do is look at the size of the elements. And so this is where you need to understand your trends from the periodic table. Okay, so looking at the periodic table, we have sodium and rubidium that's down beneath it, and we have chlorine and iodine that's down beneath it. So size gets larger as we go down the periodic table. Therefore, in terms of the size, sodium is smaller than rubidium and chlorine is smaller than iodine. Therefore, rubidium iodide has the larger ionic radius than sodium chloride. And since we know the larger the distance, the smaller the energy, that means then that the rubidium iodide has the smallest amount of lattice energy. Now, if we take a look at their melting points, then we see that those are correlated to the lattice energies. So very frequently we'll ask you, instead of saying rank them in terms of their lattice energy, we might say rank them in terms of their predicted melting points, but they are the same trend. Okay, last question. Which process would release the most energy? I want you to pause and try this one on your own. Try this one on your own, and then come back and we'll talk about it. Welcome back. So we want to know which one's going to release the most energy. So the first thing here is to recognize that A and B both absorb energy. The reason for that is that because we're breaking ionic bonds. The amount of energy here we would call the lattice energy. C and D, these are going to release energy. And the reason for that is because we're forming ionic bonds. We're going down in energy. You can think of this as just the opposite process. Since we know it takes energy to break bonds, it must give off energy to form bonds. Now, how do we know which one's going to release the most energy? Well, take a look at the size of the elements. Fluorine is smaller than chlorine. Because it's smaller than chlorine, then the lattice energy is going to be larger. Because it has a larger lattice energy, the reverse process, forming that covalent bond, or ionic bond, is going to be more exothermic than in the case of sodium chloride. And therefore, we see that C, the formation of the sodium fluoride, is going to release the most energy. Okay, that's it. Thanks for watching. Have a great day.